Let's get this puppy up and get going. One thing I realized too, I was remembering one of these chapters, 6, 7, or 8, there was one where I realized that the sections, at least in my view, were out of order. And it's this chapter. So you guys would have noticed on the, what do you call it? The module, by the way. So on this module, you'll see that I have the 7.1 reading, 7.1 lecture, but then you'll notice the next one is 7.3. That's intentional. So that wasn't just a mistake on my part. 7.3 really follows pretty directly actually from 7.1, and there's some proof stuff in 7.3, but we don't really get to it. So basically it's actually much easier and better to do 7.3 right after 7.1, and then we'll go back to 7.2 from there. So that's kind of why you see it that way. So also what I'm trying to say is, so this will be the lecture over 7.3, not 7.2. We'll do 7.2 last, but again, that's intentional. 7.1 you'll see comes straight into 7.3. So, all right. So let's start. This is another section too that, I mean, we'll see, but I don't think I have to do much. We really don't have to do many problems besides the reading. It really comes straight off what I gave you for the reading. So let's dive into that. Although let me look at this. Yeah, we may have to do one more other than the reading, but that's about it. All right, so let's start with exercise 2. Again, this is section 7.3. Bring that up. So in exercise 2, it says what she wanted you to do is in each of 1 and 2 functions f and g are defined by the arrow diagram. So we start out just like we did in 7.1. So you'll kind of see as we go through this too. I mean, literally, even the way she lays out the problems mirrors exactly the way she laid out the problems in 7.1. So these 2 sections just really pair right off of each other. So in each of 1 and 2, functions f and g are defined by arrow diagrams, and she wants you to find g compose f and f compose g. So what we're going to talk about, and then determine if they're equal to each other. What we're going to talk about in this section is function composition. So again, this is an operation on functions, another thing that you've already seen. So you've already done this in college algebra. And I don't think you really had to do this much in calculus, but you might have even referenced it a little bit in calculus. But you did this in college algebra or whatever algebra you took. So maybe you came into college at pre-cal or calculus. But you definitely did this in algebra before. So again, the way you want to approach this is I'm not going to even tell you, I'm not going to reteach you what composition is. You know what composition is. Now we're just going to do function composition with examples, just like we did in 7.1. So again, this is why these pair so well. They come, 7.3 comes right off of 7.1. Again, we're going to do something you already know about functions, function composition. We're just going to do it with functions with a little broader context that are not so algebraic. So we'll start with functions that are defined using arrow diagram. And so even though you have the picture in front of you, for function composition, I find it really important. I was talking last time about how the diagrams, the visuals on this, the arrow diagram, were actually much more important in theoretical mathematics than you would expect, and definitely compared to college algebra and calculus. But especially for function composition, the arrow diagrams and just the visuals in general are really, really useful. So let me write these functions up. So we have 2 functions that go from x to x. This is the function f. These are functions, so 1, 3, and 5. 1, 3, and 5. F takes 1 to 3. What do you call it? F takes 3 to 1. And f takes 5 to 5. So that's function f. And then function g is also going to be from x to x. And function g takes 1, 3, and 5 all to 1. That goes to 1. That goes to 1. That goes to 1. This is function G. She seems to get a little obsessed with what are these functions that all take your domain all to one element. Haven't figured out why. So you just can tell she has a lot of intention in all these problems and the way she writes them. So haven't figured out why she likes these functions yet, but all right. So the first thing we want to figure out is F compose G. And if you remember the way you want to think about function composition, one good way to think about this is that when we do function composition, what we're doing is we're taking X and plugging it into G and then getting our output. So we're taking the input, whatever input we want to start with, we plug it first into G. And then whatever output we get on that becomes our input in F. So it's your input goes into G, you get a number out, that gets sewn back into F, and then you get a number out of that, and that's your true output. That's your output for F compose G. So for F compose G, what we can do, and these are X, is we're going to go back to our arrow diagrams here, and we're going to trace this action. So for F compose G, we're going to start with with all three of our inputs, so 1, 3, and 5, but we're going to start in G. So let's start with 1. So for F compose G, if I plug in 1, where I'm plugging it in first is G. So I'm going to go to G, and if my input is 1, what is my output? Good, that's 1. So 1 goes to 1. Now that output becomes the input on F. So on F, if I input 1, what do I get? Good, I get a 3. So 1 then goes to 3. I put in 1, G turned it into a 1, and then F turned that 1 into a 3. So overall, I put in a 1 here, I got out a 3 here. Good. Now let's do F compose G of 3. So let's put in a 3. If I put in a 3, then for F compose G, I start with G. So if I put in a 3 here, what do I get out? Good, I get out a 1. And then I put that 1 into F, and what does that give me? That also gives me a 3. So I put in a 3 to begin with, and I get out a 3. So 3 goes to 3. Good. Seeing a pattern here. So now let's do 5. So F compose G of 5. So I put in a 5 to G first. So I put in a 5 to G, and what do I get out? Good, that gives me a 1. And that output then becomes my input on F. So I put in a 1 to F, and what do I get out? Good, again, I get a 3. So 5 also goes to 3. So this is the function F compose G. And that's what they're looking for here. So as a note, anytime they're asking you, what do you call it? So like in 7.1 in the last section, they were asking things like domain and range and things that were all sets. And so we gave our answers as sets. But when they're asking you to give the answer of, when they're asking you to create a function or asking what a function is, so you could, by the way, one of the ways you could have given the answers here is you could have given ordered pairs. But in general, what they like to see is if they give you the function as arrow diagrams, then they kind of want you to give the answer as an arrow diagram. Now, obviously at this point in mathematics, you don't have to do that. You can give the function any way that reads as a function. So I made a decently big point last time that functions at their essence are just sets of ordered pairs. So you could always give a set of ordered pairs for a function. But because we have these visuals to begin with, because we start with arrow diagrams, it might make a lot of sense and be pretty easy for you to give the answer as an arrow diagram. So let's do the other one then. So we did F compose G. Now we want to do G compose F. And you don't have to put it in parentheses with an X. I'm just doing this more for the visual. Again, what G compose F means is now my inputs from X, I'm going to put those into F first. And then whatever, so I'll put the input into F, that'll give me an output. Whatever that output is, I then put that back into G. And then the output I get from G now is my, what do you call it? Is my output for the function. That's my output for G compose F. So pick an X. So again, what we're gonna do is we're just gonna do 1, 3, 5. We're gonna follow each one. We're gonna pick a 1, put it in to F, and then put that result into G, and then whatever we get out of that, that's my output. So let's start there. So I want to do G compose F of 1. So if I put a 1 into F, what does that give me? What's the output? The output is 3. Good. So then I'm going to take that 3 and put it in G, and if I put a 3 into G, what do I get out of that? Good, a 1. The 1 goes to 1. I put in a 1. It became a 3 momentarily, but then that 3 became a 1 again. Now let's do the same thing with 3. So I'm going to put a 3 into F to begin with. So in F, 3 becomes what? That becomes a 1. And then that 1 goes into G, and that 1 becomes what? Also becomes a 1. So I put in a 3 to begin with, and I got out a 1. And then what about 5? G compose F of 5. So I put a 5 into F. What does that become? Good, that becomes a 5. And then I put that 5 into G, and what does that become? A 1. So 5 goes to 1. So it's kind of interesting. So G compose F is actually just G. It's the same function, which more happened is more random that it happened. That doesn't often happen, but it does here. But this would be G compose F. And that's what we're looking for in something like that. They also asked you as part of the problem or part of the question, they asked you whether G compose F equals F compose G. So, okay, good. And so does G compose F equal F compose G? Are they the same function, same order pairs? No, yeah, so you can then consider. It's pretty obvious just looking at these that F compose G does not equal G compose F. Good, so we can compose functions with arrow diagrams. All right, the next thing I gave you. Oh, yeah, so I did give you 3. So in 3, so the next reading sum or problem in reading you had to do was number 3. But in 3, I gave you these functions more traditionally like you saw in an algebra class. So these are polynomials, but they're just our usual x cubed x minus 1. So here we wanted to compose these. And so here, so again on 2, if I give you arrow diagrams as functions, the arrow diagrams are useful for you getting your answers, but really that's also giving you the tip that you want to give your answer as an arrow diagram. So then on 3, especially here, if I give you your functions as equations, then you want to give your answer as an equation. And you'll see actually in this, again, you could do a set of order, you could try to do a set of ordered pairs, and it would be one of these sets that has a dot dot dot, in it because it's an infinite set of ordered pairs. So you could try to do it as that, but really the not only best way, but easiest way to represent this is actually the equation. So they give you equations for functions. You want your function composition to be an equation. So let's look at that. Second. All right, so in 3 here, f of x, capital F of x, that's special. But capital F of x is x cubed. Capital G of x is x minus 1. And we want f compose g and g compose f for each real number x, but we want f compose g and g compose f. So now f compose g. Again, if you remember from your algebra class before, that literally means do f of g of x. So this means f of g of x. So when we don't, so on the last one, we had our, we call it our domain and codomain were sets, discrete sets of numbers. They were sets of, just very particular numbers. But here my domain and codomain is all real numbers. And so on the last one, we were able to physically plug a number in and kind of trace its result. But here we're not going to be able to do that because we don't have an infinite amount of time. So instead, the way you want to think about this is literally, so f compose g of x means f of g of x. And that literally means to put g of x into f. So in f, everywhere you see an x, you're going to replace it. You're going to substitute g of x there. So in f, everywhere I see an x, instead of an x, I'm going to write x minus 1. Because I'm just using this functional, I'm using the, not just the idea, but I'm using the functional notation. Give me a second, y'all. Hello. Yes, there we go. How's it going? All right, we're back. Thank you guys. But yeah, so when I say something like f of g of x, I'm using that functional notation that you're used to, where whatever's inside the parentheses is literally telling you what to plug in. So I'm literally plugging in g of x, which is x minus 1, into f. So that's x minus 1 cubed. And for the sake of this class, you can just leave it there. There's no, you don't have to multiply that out or anything like that. That's a perfectly fine looking function. So that's f compose g. G compose f then is going to be plugging f into g. G of f of x. So in g, where I see x, I'm going to plug in f, which is x cubed. So this is going to be x cubed minus 1. And that's g compose f. And then this problem, like the last problem, asks if they're equal. And obviously, these are not equal to each other. Just the difference in the order of operations is enough. They're not the same. Good. All right. Let's keep going. We're just basically, as far as I remember of this work, we're literally just going to keep doing a lot of the same, but just again, just functions of different contexts, different types. But all similar to what your types of functions you saw in 7.1. So, oh, 2, 3, 6 was the next one. So 6. So here we have two functions, f and g. So f is from integers to integers, so domain and codomain are integers. And g is also going to have to be the same. Defined from integers to integers. Technically doesn't have to be exactly the same, but and so this is the more general way that we were defining functions from that you got used to in 7.1. This function is defined by the rule that f of a equals 7a. G is defined as g of a equals a mod 5. Good. And then we had several things to find here. So let's just kind of do these in parts. They didn't list it as A, B, C, D, but I'm going to do that just to visually give some separation. So we got G compose F of 0. Let's work that through. So G is throwing in that little mod 5 that we got used to throwing in the last section 7.1. G compose F of 0. Again, if I give you a specific number, then all I'm going to do is plug 0 into F. And whatever result I get there, I'm going to plug into G. So let's plug 0 into F first. So if you plug 0 into F, 7 times 0 gives you 1. That gives you 0. And then if you plug 0 into G, 0 mod 5 is equal to 0. So G compose F of 0 is 0. And I guess they're just doing a bunch of G compose Fs here. I wonder why they focused on that, but that's fine. So G compose F of 1. G compose F of 2. G compose F of 3. G compose F of 4. So let's go through this. Plug in a 1 to F. So 7 times 1 is 7. And then what is 7 mod 5? So you should have got 2 for that. G compose F of 2. So 2 into F. 7 times 2 is 14. What is 14 mod 5? That's going to be 4. Then we'll do 3. 7 times 3 is 21. What is 21 mod 5? Good, that's a 1. And then finally on 4, 7 times 4 is 28. And what is 28 mod 5? That's a 3. And you've got it. So 0 gets mapped to 0, 1 goes to 2, 2 goes to 4, 3 goes back to 1, and 4 goes to 3. There's some interesting diagrams you can make with that we'll actually see a little bit in the next chapter on relations, but also if you ever take a class called abstract algebra, they make interesting diagrams out of something like that in terms of related to something we call groups. So groups and what do you call it, rings and cyclical groups. All right. But just get you to play with not just algebra, but modular arithmetic. And then we have 8a and 9a. Make sure. And we may not have to do much more than that. It looks like 8. Well, 8 is a fun mix of different types of functions. Let me see if I can find a quicker way to write this down. Maybe I can't. So an 8. L is a function that's from S, and we're going to use S. We're using S as the same set we saw in 7.1. S is the set of strings using A's and B's instead of zeros and ones. That function goes to the integers. And they say that this is the length function. So what they mean is L of S equals the number of characters in X. Number of characters in S. So literally just the length of the string. Count up all the characters. And then T is this function from the integers to the set 0, 1, 2. And they're saying this is the mod 3 function. So T of n equals n mod 3. Just whatever the remainder is after you divide by 3. And notice that the codomain, the set that you're going to here for the function, is the possible remainders after you divide by 3. You can either have a remainder of 0, 1, or 2. You can't have a remainder of 3 because then it's divisible by 3. And so you have a remainder that's actually just a remainder of 0. So these are my two functions. A, easy enough. We want T compose L of the string A, B, A. And again, these functions are funky. This looks funky to write all this in there, but it's the same exact thing you just did. Literally what they're trying to do in these two sections and in this chapter is really get you used to all the things you did for functions. You can do those no matter what the context is. It actually just isn't any different. You don't have to play any different games with them. So this is not somehow different because we're talking about strings or modular arithmetic or any of that. Function composition is not different. All I'm going to do is plug this into L. I'll get a result out of that, and whatever results out of that, I'll plug it into T. Works just the same exact way you do if these were algebraic functions. So let's plug it into L. So we want L of ABAA. And L again is the number of characters. So what is L of ABAA? So we'll just kind of do this in steps. Well, I don't want to write it out that way. So L of ABAA then is 4. So you get a 4 out of that. It is 4 long. And then we're going to plug 4 into T as a mod 3 function. So what is 4 mod 3? Good, that gives you 1. And you got it. Why are those two functions being composed? I don't know. And thankfully, actually, it doesn't even matter. I don't care. I can compose them. So again, what it's trying to show you is no matter what weird context these functions are, how general these functions are, function composition is an operation. It's an action on functions that I can do as long as the two things are functions. It actually really doesn't matter what the context is. So again, why would I compose these two functions? Yeah, doesn't matter. No importante. Está bien. That's 8a. I also wanted you to look at 9a. Especially 9a, I wanted to remind you of a function that, again, you probably saw in college algebra, but actually they use it much more in calculus. So you probably haven't seen it since the calculus class. So f is a function from R to R. And it is defined by f of x equals x squared over 3. Fine enough. And then g is a function from R to z. So by R, I mean real numbers. So let's put the double back on all those. The z. And here, g of x equals the floor of x. So if you haven't, again, if you saw this symbol somewhere in calculus at the least. Oh man, and I'm drawing it wrong. Let's try this again. One stick, hockey sticks. Sometimes that's how I remember how to draw stuff. Just in my mind, shout out the object that it looks like. It's actually a similar idea. That's actually how I learned to draw an infinity sign. I couldn't draw it, and then I was just like, oh, it's just an 8 laid on its side, and so then I took like 3 weeks of carefully practicing drawing an 8 on its side, and voila, infinity sign. Anyways. So this is the floor function of x. So there was a floor and a ceiling function. And remember, the floor function basically literally means round down. So it's an automatic round down to the nearest integer. And the ceiling function means automatically round up. For the ceiling function, you'll see the same sticks but flipped over, so that you have literally a ceiling above the x, whereas here we have a floor below the x. So that's why they call it floor and ceiling. But floor function means you automatically round down no matter what. Ceiling function means you automatically round up. So then on part A, I wanted you to do G compose F of 2. Again, this means I'm going to plug 2 into F, get some result, and then I'm going to take that result and plug it into G, get some result from that, and that is my output. So let's start with F. 2 gets plugged into F. 2 squared is 4. 4 divided by 3 is 4/3. You don't have to necessarily turn that into a decimal. The decimal would be an approximation anyways. But we get 4/3 or 1 1/3. And so that's my output on F. That's 1 1/3. And then I'm going to take that and plug it into G. So I'm going to take 1 1/3 and I'm going to do the floor of it. So I want the nearest integer below it. And so what's that going to be? Good, that's going to be 1. So the answer here is 1. Good. Just remind you how to mess with floor and ceiling functions. And let me just make sure we don't need to do anything else with this section. Actually, no. In terms, and also you saw other types of functions last time, cross products, ordered pairs, that kind of stuff. So those might be in play, but actually this covers everything that I really want to get out of this section. I didn't want to do the proofs in this section. Because they're cool, but they're a good bit more complicated than the ones in 7.2. And really the ones in 7.2 are the ones that I want you to be able to focus on. So we'll see in this next lecture, we're going to do 7.2. There's 2 important concepts that, again, you already know about functions, one-to-one and onto. But we now want to look at how do we prove that these funky functions with weird context, or just functions in general with no context, that they are one-to-one and onto. And so when, again, in a college algebra class and a calculus class, you just sort of identified by eye whether they were one-to-one and onto. Now we want to prove that they are one-to-one and onto, and maybe prove some patterns and properties about things being one-to-one and onto. So that's what we're going to look at in 7.2. And I really decided at some point that especially for this class, teaching it here where I'm not teaching mathematicians in general. So there's a couple of y'all this semester, but in general, I'm teaching computer science majors. I really want you to focus on just you being able to do the proofs for one-to-one and onto. And if we can get that, then you're golden, you're good. So we'll do that in 7.2, but this is it for 7.3. So I'll see you guys on the next lecture.
Mm.